Hello everyone, my name is Jiseon Kim. I'm PhD candidate at Postec. Today I'm going to talk about my research area, nickel-based mixed metal oxyhydroxide electrocatalyst for direct urea oxidation. First, I will discuss why focusing on urea oxidation reaction. So I'm going to divide perspective into two main parts. First, pollutant treatment. Urine is a major component of urea. This urea is the abundant nitrogen carrier. So if urea is not properly treated, the excessive nitrogen from toilet wastewater causes to environmental problems, such as eutrophication of surface water. This means the UOR enables the urea decomposition to solve this problem. Second perspective relates to energy conversion. In electrochemical system, hydrogen evolution reaction occurs at the cathode side. This electrochemical produced hydrogen acts as a clean energy carrier. So there is thermodynamic advantage of using the UOR at the anode instead of oxygen evolution reaction. Comparing thermodynamical cell voltage, then using the urea splitting is recommended. Also, direct urea fuel cell is one of the promising methods because this system enables simultaneous wastewater treatment and electricity generation. So I focus on urea oxidation reaction. However, this UOR contains 6 electron transfer process, which lead to a slow kinetic rate. So UOR require the properly electrocatalyst. Many researchers found that nickel is the best electrocatalyst. Nickel is also abundant material, so it is available. And even compared to noble metal, nickel has better UOR performance. Further design strategy of catalyst is the incorporation of additional metallic elements. It can enhance nickel-based catalyst through bimetallic synergetic effect. So many preceding studies have suggested that various transition metal-based powder electrocatalysts are loading on conductive substrate by electrodiffusion and hydrothermal growing methods. These attached catalysts can easily fill off from the substrate during dynamic gas evolution. Therefore, to adopt in real application, electrocatalyst stability is a growing problem. For this reason, now I intend to focus on the issue of in situ or ex situ oxidation or by etching process of commercial alloys. These alloys are made up of nickel and iron and cobalt. So there are some studies alloys can utilize both as a current collector and catalyst source to create freestanding electrocatalyst through the collision engineering. Therefore, this study examined various commercial alloy materials as an electrocatalyst by using electrodissolution method. Based on fallback diagram, there are thermodynamically stable phases of an aqueous electrochemical system. Therefore, in this system, different types of commercial alloy were activated by potentiostatic de-alloying method under certain pH conditions. This approach can some elements selectively separated and removed from the alloy, so a surface with a new composition can be formed through electrodissolution method. Then how should we evaluate the UOR performance using activated alloys? First, look at the cyclic stoichiometry graph as an electrochemical analysis. The current response absence and presence of urea in the solution Addition of urea in the solution, then current is considerably increased. This current difference can be estimated by UOR. In more detail, first, when urea is in the solution, compare the current value obtained at specific voltage at 0.6 volt. Secondly, peak current value can be obtained from current difference depending on the urea. Finally, the amount of integrated charge of current difference can be determined to estimate how much urea oxidation reaction occurred. So this slide shows the result of UOR performance. First of all, this photograph can be simple evidence that surface transition occur by changing the surface color after potential static de-alloying methods under 3 types of pH condition. Actually, as shown in the graph, UOR activity were evaluated with 3 parameters. Here is the UOR activities show large variation depending on source material and de-alloying pH. Using the 3 indicators, each result shows that the rich base material treated in neutral pH has the highest UOR activity. And to take if the 3 evaluation indicators are valid, let's find out the correlation between each parameters. This linear regression implies that all parameters are correlated with others. In short, use of these 3 parameters are effective to explain the UOR activity. To find out more detail about UOR is more energy efficient than OER, the graph shows the highest activity of treated alloy depending on other source material respectively. At specific applied voltage, obtained current densities show much higher value in urea splitting than water splitting. This means that the use of urea electrolysis can be possible more hydrogen production because UOR has a thermodynamic and kinetic advantage. As shown in set graph, the secondary elements can affect the nickel oxyhydroxide formation. In more detail, when urea is in solution, current increases from near the voltage of nickel oxyhydroxide formation. This result means that nickel oxyhydroxide is the main catalyst for UOR, so formation of nickel oxyhydroxide is also important. So it is important to find out why UOR activity has increased. First of all, only the treated nickel-rich base material group was evaluated. Using scanning electron microscopy, variation of morphology were observed. When treated at neutral pH, severally grouped morphology were clearly observed. This results in an increase in surface area that can offer more active reaction sites. In addition, the surface phase composition of the treated electrode was analyzed by Raman spectroscopy. In neutral pH treated electrode, the Raman bands are related to gamma nickel oxyhydroxide and layered double hydroxide peak. Therefore, the form of oxyhydroxide or hydroxide can affect the increased UOR activity. To further identify the chemical state of the surface of treated alloy, X-ray photoelectron spectroscopy analysis was performed. The high-resolution nickel spectrum can be convoluted into 3 types assigned to nickel metal and nickel oxide and nickel hydroxide and oxyhydroxide. In here, the metallic nickel peak of treated at neutral and basic pH conditions have almost disappeared due to the successful generation of metal hydroxide and oxyhydroxide foam. This result is consistent with the observation in the Raman spectrum. Therefore, to find the reason for the increased UR activity, I calculated the surface concentration of redox active nickel center. Then this value was extracted from the slope of the linear relationship between the peak current of the reduction wave and scan rate. Accordingly, the coverage of redox active nickel center has the largest value for treated in the neutral condition electrode. Until now, the factors affecting the increased UR activity are largely divided into two parts. First, increase the active side, and second, create hydroxide and oxyhydroxide foam on the surface. Therefore, in order to find out which factor further affects the UR activity, the current density was divided by active nickel center. The normalized current shows that electrodes treated under basic conditions shows the highest activity. This means that the intrinsic activity was the most increased when treated under basic condition. Here, the sum of the result, the active site increase has more impact on performance improvement. In addition, urea oxidation reaction can also be used in direct urea fuel cell, and the system configuration is as shown in the figure. Thermodynamically, a combination of oxidation and reduction reaction leads to a spontaneous reaction. Direct urea fuel cell can possible to current generation without energy supply. So, treated electrodes exhibit the highest power density, which means that efficient UR leads to an increase in power generation. Now, I'd like to sum up the main points of my presentation with the following observation. First, I covered that the improvement UR activity enables through potential static de-yellowing depending on source material and de-yellowing pH condition. Then I talk about the reason for activity increase. It related with increase of active site and formation of hydroxide and oxyhydroxide foam. Finally, we look at the power generation is possible by applying a UR to the direct urea fuel cell. Based on this result, my ongoing project is utilization of nickel iron oxalate electrodes. This project utilized a three-dimensional nickel iron alloy foam, both as a substrate and catalyst source, to create a self-supporting, highly efficient UR electrocatalyst. So, one-part thermochemical treatment of the nickel iron foam by oxalic acid solution then generated prismatic nickel iron oxalate. These electrocatalysts exhibit excellent UR activity that promise energy-saving hydrogen production. And second ongoing project is combination of direct urea fuel cell and forward osmosis membrane. Power generation is unstable when using only direct urea fuel cell due to the decrease in urea concentration. To solve this problem, forward osmosis membrane was adopted, then continuous production of electricity and treated water are possible. Thank you very much for your attention. If you have any question or any comments and suggestions, please feel free to email me. Thank you.